Hello everyone, welcome to the NPTEL online certification course on fundamentals of food process engineering. Today we will start a new chapter on freezing and freeze drying. We have just now seen in the previous chapters one important unit operation, that is drying, and drying is as we have mentioned that it is a method of preserving the food by lowering the water activity to the safe storage level. Similarly, freezing is also one very important operation by which we can store or preserve the food material for longer duration of time. However, the difference is that freezing is a low temperature preservation. So, in today's class we will see that how this freezing operation is being done on different food material. So, if you have seen the various kind of fresh fruits and vegetable markets where storage of fresh fruits and vegetable are being done. So, you might have seen that freezing is the most common operation, and mostly in the shelf of the storage, frozen products are kept for longer duration, and the advantage is that when we freeze the material and after certain time of storage, if you want to reuse it, so we can get the initial quality and the structure of the food intact. So, that is not available if we preserve them by drying. So, drying causes shrinkage and case hardening and the deterioration of the structure, quality, flavor, color, etc., whereas freezing can preserve those quality very well. Therefore, it is a very important operation, and not only for fruits and vegetable, freezing is very common for the muscle foods such as fish, meat products, etc. So, thereby freezing is very important. Now, another low temperature preservation that we sometime do, the term is chilling, but the difference is that chilling and freezing, in both the cases we lower the temperature, but chilling is done above melting point and freezing is done below melting point. Okay. So, this is the a little bit overview of that. Now, in this chapter we will cover the concept of food freezing, freezing time calculation by Planck's equation and Pham equation, different types of freezer, quality changes during freezing. So, first we will see the definition and concept of food freezing. So, freezing involves changing physical state of substance by converting water into ice by cooling below the freezing temperature. Okay. And also one thing I must mention here is that when we do drying and after that we can preserve the product at normal ambient temperature, right, because the water activity is so low. So, generally the contamination does not take place, and also we can keep at certain temperature and relative humidity, and based on that combination we can decide what is the safe storage moisture and we can dry up to that level. However, if we dry by this method, if we preserve by freezing, okay, so then we need to keep the condition or the temperature intact till we consume the product. If the fluctuation of temperature happens, then again the ice phase to water phase conversion will be there, and it will cause some undesirable changes in the quality of food. Therefore, for frozen storage we need to maintain the cold chain throughout the production, processing to the consumption. Now, by freezing we can control the physicochemical and biochemical reaction that deteriorate the food quality. Now, this reaction minimized because by conversion of water to ice we restrict the mobility of the liquid water, and along with the liquid water what are the dissolved solid and enzymes. So, all those restricted to some certain location. So, their mobility is restricted, and because of that the changes will be minimal. However, variation in storage temperature and duration imparts slow and progressive changes in organoleptic quality. That means, while performing the freezing operation, if we perform the slow freezing or we perform fast freezing, quick freezing. So, both the cases formation of ice crystal or the structure will be different, and they will affect the food quality in different way. Okay. So, freezing process immobilizes the random motion and rearrangement of molecules in the matrix, hence water is not readily available for microbial growth. So, not only chemical reaction, but microbiological reaction is also minimized. So, the difference from the previous method is that in case of freezing we are not removing the water, but we are restricting the mobility of the water by converting the water phase to ice phase, and thereby we can keeping the moisture of the product intact. So, when we want to consume it, we thaw the product, we bring it to the normal ambient temperature, and then we can get the initial quality, almost the initial quality of the food. Freezing curve for water and food. Okay. Now, before describing the curve where we have plotted the temperature versus time, okay, and how these changes happen from one stage to the other, let me first explain you that how this phenomena of freezing normally takes place. That let us say this is a container, okay, where this part is ice, okay, and here the liquid water is there, right. So, liquid water molecule will liquid water and this ice in this closed chamber will try to come to an equilibrium situation. So, what will happen that the liquid will come to the interface, this ice and water interface, and it will try to convert to ice. So, the latent heat of fusion will be released and similar molecule will convert from ice to water. Okay. So, this process is going on when it comes in the equilibrium situation. But what happened, the mobility in the liquid water is quite high, molecular mobility in the liquid water is quite high. Okay. Now, when we try to lower the temperature, then what happened? So, initially the molecules, those were in random motion, will try to restrict the velocity. Okay. As temperature will lower, they will try to have minimal movement and come very close, okay, very close to each other, and after certain time they will try to form aggregation. Okay. So, what happen? The molecule will form certain aggregate in places, and that is the onset of nucleation, from where again when this aggregation will attain minimum amount of diameter. Okay. So, then further crystal growth will start from this place, and as we lower the temperature, so freezing will be there. Okay. So, this is how freezing takes place as we lower the temperature. So, from the liquid water to frozen state it will become. So, now let us look into the plot of temperature versus time. So, this upper plot, this is for the pure water, and the lower one, this is for the food material. So, what will happen? First, look into the point A to B. Initially, when we are taking liquid water and we are lowering the temperature of liquid water, so sensible heat we are extracting. So, with time the curve A to B showing the decrease in the temperature because of sensible heat removal, and also the food is cooled below freezing point, that is lower than 0 degree, and here the nucleation process starts. Nucleation as in the association of the molecules into teeny ordered particle sufficient to survive and serve as a site for the crystal growth, as I have just shown you that how those aggregation formed as lower temperature. So, at point B for in case of the food sample, this nucleation starts. Okay. So, then we will go to the next section, that is B to C. We can observe in both the plot for pure water and for the food sample, there is a little bit increase in the temperature from B to C zone. This is because the latent heat of crystallization. So, as the crystal form, heat will be released, latent heat of crystallization will be released, and that will enhance the temperature of the food a little bit. So, slight increase in the temperature from B to C is observed here. So, latent heat of crystallization is released and thus temperature rises rapidly to the freezing point, giving off the latent heat of fusion, and ice now starts to form. So, once nucleation happen, that is the first crystal formation is being done, then it starts increasing as we further lower the temperature. Now, ideally the phase transition should happen at constant temperature, that is 0 degree for pure water. So, if you look into the pure water plot, there is not much change in the temperature. However, in the case of food material, we can observe a gradual decrease in the temperature. This is because you can remember that while discussing evaporation, we have mentioned that boiling point elevation occurs when the solutes are dissolved into the water. Okay. Similarly, here what happened, that when the liquid will convert to ice, so as the concentration of the solutes in the food material, they will start increasing because less water available and solute concentration were the same. Okay. So, water has been converted from liquid to ice. So, that remaining liquid become concentrated in the solution, that in the solute concentration, because concentration will be similar. So, because of that the freezing point of the water will be lowered. So, that is why freezing point depression occurs in this case for the food material. So, C to D, major part of ice formed here. In unfrozen liquid, there is an increase in the solute concentration, that is why temperature falls slightly. Okay. Now, coming to the point D to E, see this kind of thing is not available in the pure water. So, this property, that is because of only the food material or a mixture kind of material, we can observe this kind of behavior. So, one of the solute becomes super saturated and crystallizes out. Latent heat of crystallization is realized and the temperature rises to the eutectic point of the solute. So, eutectic point means the lowest melting point of the eutectic mixture. And what is the eutectic mixture? It is that when we mix two components and those are not reacting with each other, but they can mix properly and create an uniform mixture. In that case, if we try to freeze it, So, what will happen that the minimum temperature that at which the melting will occur. So, that temperature is considered as the eutectic temperature. So, we can observe at point E this eutectic temperature, and then point F to G. So, till F all the food has been, all the water has been frozen, and then from F to G shows the sensible cooling of the frozen material. Okay. So, temperature of the ice water mixture falls to the temperature of the freezer, and percentage of water remain unfrozen. So, if a little bit of unfrozen water remains, because it has become so much concentrated, so its freezing point will be lowered to a higher extent, and food frozen below point E forms a glass which encompasses the ice crystal. So, the concept of ice crystal growth and nucleation, if we want to understand that. So, water ice transformation leads to crystallization, that is formation of systematically organized solid phase from the solution, that is basically of the solute and water. Nucleation, as we mentioned, that these are the molecules into teeny ordered particle of size sufficient to create the growth of the crystal over their surface, and initial freezing point temperature is such that at that temperature a teeny crystal of ice can exist in equilibrium with the liquid phase. So, as I mentioned in the in that diagram, that initial freezing point, that means at which the crystal of ice can exist in equilibrium, that means how much liquid will convert to the crystal, a similar amount is converting to the liquid water. So, that condition arise, and then we further lower the temperature, and then the ice formation will increase. So, two types of nucleation we can observe, homogeneous and heterogeneous, or catalytic nucleation that occurs in food materials, which involve formation of nuclei adjacent to the suspended foreign particle surface film on the wall of the container. So, these are the places where some induced nucleation may happen. Crystal growth, it occurs just below the melting temperature and at near to the melting point, because crystal growth happens below the melting temperature, that is why we have received one supercooling before formation of the ice crystals. Okay. So, then crystal formation will start and little bit temperature rise we have observed. So, at near to the melting point temperature, the addition of the water forms new nuclei, and more the nuclei forms, the solute concentration increases. Crystallization is governed by heat and mass transfer rate. So, because heat transfer is important, because the rate at which we remove the heat or the lower the temperature. So, that causes the nucleation and crystal growth. And if we visualize that rate of nucleation with temperature, so we can see that from 0 to minus 40, that means we lower the temperature, and at some point when the rate of nucleation happens, then this is the initial supercooling point. So, then rate of heat removal, that means when this nucleation starts, and then its rate will propagate as we move on to further lower temperature. And here in the second picture we can see the rate of crystal growth with temperature. So, once the crystal growth has occurred, because it has occurred not nucleation occurred lower than the 0 degree. However, once the formation of ice has been done, it will start from the 0 degree and it will go up to as low as minus 40 or minus 50, because as the water will be freezing, solute concentration increases. So, eventually the temperature will also decrease. So, rate of nucleation and crystal growth with temperature. Rate of ice crystal growth is generally not limited by mass transfer process except during the later stage of freezing, when temperature is low, viscosity is high and unfrozen water is low. That means, initially we have mentioned that it is governed by both the transfer process. Now, rate of ice crystal growth is generally not limited by mass transfer. However, this will be limited by the heat transfer process. Heat transfer limit the rate of crystallization because of large latent heat of crystallization of water needs to be extracted from the material to cause the freezing of the water. So, growth rate is increased greatly with increase in the heat removal. Therefore, at this stage heat transfer causes the higher effect compared to the mass transfer. So, we will stop here, we will continue with the freezing process in the next class. Thank you.